Hello! In this video, we're going to focus on the concept of escape velocity. So, just to make this clear before we do anything, escape velocity only applies to unpowered projectiles. So, a rocket, for instance, which is powered by fuel, hydrogen, does not count as an unpowered projectile, so the concept of escape velocity does certainly not count. So we all know that the faster a ball is thrown upwards, the higher it rises before it is stopped and pulled back by gravity. In this video, we will show by calculus that to escape from the Earth into outer space, an object must have a speed of just over 11 kilometers per second. This is known as the escape speed. So the escape speed is obtained from the fact that the potential energy gained by the body equals its loss of kinetic energy if air resistance is neglected. The work done measures the energy change. So what we're going to do is let little m be the mass of the escaping body and capital M be the mass of the Earth. So the force F exerted on an object by the Earth when it is distance x from the centre of the Earth is gmm divided by x squared. Okay, m is the mass of the Earth, little m is the mass of the body, and x is simply the distance from the centre of the Earth to the body. So therefore, the infinitesimal work done by gravity when the body moves a further short distance delta x is minus f delta x. Okay, this is the same as saying work equals force times distance, but this is an infinitesimal work done, which is equal to your force, or your negative force, multiplied by an infinitesimal distance x. Okay, and of course our force is equal to gmm over x squared, therefore we can rewrite the equation as minus gmm divided by x squared multiplied by delta x. Okay, so the negative sign shows that the force acts in the opposite direction to the displacement. Okay. So to find the total work done while the body escapes, we simply need to integrate using an integral. So this is equal to the integral from r to infinity of minus gmm over x squared times dx, okay? Where r in this case is the radius of the Earth, and because the radius varies for every body, we integrate it from r to infinity. So we can pull out the constant minus gmm, and what we get when we compute the integral is minus gmm multiplied by minus 1 over x evaluated from r to infinity. Okay. Right, so we can calculate the minuses by multiplying by minus 1. So this is equal to gmm multiplied by 1 over x evaluated from r to infinity. So as we know, this is equal to minus gmm over r, because if you put infinity into x, we just get 0. So we get minus gmm over r, which of course, as you know, is our gravitational potential and our work done, as it seems. Alright? So if the body leaves the Earth with speed v and just escapes from its gravitational field, therefore, we can say the kinetic energy is equal to the work done, which is, of course, the conservation of energy. So kinetic energy, or half mv squared, is equal to our work done, gmm, divided by r. So we can rearrange the equation to find for velocity. Velocity, therefore, is going to equal the square root of, let's see, multiplied by a 2, so we get 2gm divided by r, and the little m's cancel, which is of course the mass of the body. So that obviously implies that it doesn't matter what the mass of the body is, it's still going to have the exact same escape speed. Okay, but as we know, our simple equation g, which is 9.81, is equal to gm over r squared. So therefore, gm over r in our velocity equation, we can substitute for g. So therefore, we finally get that the velocity of our body escaping the Earth's gravitational field is equal to 2gr. Okay, that is the escape velocity. Alright, so it's good to commit that formula to memory, as it'd be very useful. So if we substitute r and g, so g for the Earth is 9.81 meters per second squared, g equals 9.81, and the radius of the Earth is equal to 6.4 times 10 to the 6 meters approximately. Okay, so if you put 9.81 for g and 6.4 times 10 to the 6, you can check this on your calculator. We get that the velocity is equal to approximately 11 kilometers per second. Okay, approximately. Alright, and that is the proof using calculus. So I hope that's pretty useful. It was fairly easy, basic calculus concepts. So we just used Newton's formula, F equals gmm over x squared. We looked at the work done, and we implied that the kinetic energy must equal the work done, and therefore we rearranged to find our velocity, which came out as the square root of 2gr, which gives us 11 kilometers per second for Earth, and for the Moon you could just simply put the radius of the Moon and its gravitational field strength. Okay, so I'll see you in the next video.